This is part 2 of further mathematical induction. In part 1 we did a review of the process of mathematical induction and looked at some standard questions. Now we're going to have a look at some propositions where maybe they're only true for even or odd values of n. So we'll do 2 examples to help us understand how to solve these type of questions. Let's get started with example 1. Show n squared plus 2n is a multiple of 8 for all n that belongs to the set of natural numbers. And this is the bit that's different from part 1, where n is even. So this is going to play quite a large role in how we do this question. It's going to change each of our 3 steps. So let's see what step 1 looks like. Prove true for n equals, well, n equals what? See, normally we'd do n equals 1, right? But n must be even. So our first natural number that is even is 2. So that's where we need to start in this case. Prove true for n equals 2. So let's go ahead and do that. N squared plus 2n. Well, we replace n with 2 and we get 2 squared plus 2 lots of 2. And that's simply 4 plus 4. And we know that that is 8, which is a multiple of 8. So nice and easy to start off with. So we can say, therefore, it's true for n equals 2, our smallest natural number for this question. Let's go on to step 2 now, where we assume true for n equals k. But we need to make sure that we state that k is even, right? So it's all well and good to say that we're assuming it true for n equals k, but remember all values of n, and therefore in this case k, has to still be even. So let's write out our statement now with k instead of n. So k squared plus 2k. Now to show that it's divisible by 8, we're going to express it as 8 lots of p. Okay, and this is for some natural number p. Alright, step 3. Prove true for n equals, well, once again I've left it blank. What do you think should go here? See, normally we would say n equals k plus 1, right? But we can only deal with even numbers. So what's the next even number after k? Well, if we just did k plus 1, that would be an odd number, wouldn't it? So we need to jump 2 more to get to the next even number. So we are going to prove true for n equals k plus 2. And let's just state why we've done that. So if k is even, then the next even number is k plus 2, not k plus 1. Alright, so what is it that we are required to prove? Well, instead of k squared, we now have k plus 2 squared, and instead of 2k, we have 2 lots of k plus 2. Once again, we want to show that this is a multiple of 8 or divisible by 8, so we'll set it equal to 8 lots of some q, where q is a natural number. Now let's start by focusing on the left-hand side. Remember, we want to use step 2 at some point. So as we're manipulating this, we want to look out for how we can involve k squared plus 2k. So let's expand this perfect square, k squared plus 4k plus 4, and then expand this second lot of brackets plus 2k plus 4. tidying things up a little bit, we get k squared. Now, we could go and combine the 4k and the 2k, but remember we want k squared plus 2k. So I'm actually going to move this 2k here next to the k squared, and we'll bracket that off because we're going to perform a substitution, and then let's write what we have left. So we have our 4k, and 4 and 4 gives us 8. Now we can perform our substitution from step 2. So 8p plus 4k plus 8. That's using step 2. However, when you look at this line, we're not quite ready to drag an 8 out the front as a common factor, which is what we're aiming to do. Right? Ultimately, we're trying to get 8 as a common factor. I've got this 4k here. So what are we going to do about that? Well, remember that k must be an even number. So since k is even, is there another way we could express k? Yeah, any even number must be 2 lots of some other natural number. So I'm going to go with m. Okay. So m is some natural number. K is even, so it can be expressed as 2 lots of m. So let's make that substitution in this line up here. We can replace k with this 2m, and what that allows us to do is get a common factor of 8 that we can drag out the front. So this becomes 8m, and so we drag that that 8 out the front, we get p plus m plus 1. And since p and m are both natural numbers, together this expression gives us some other natural number, which is in fact our q value that we're after. So here's our little link between our different sort of variables. But we have now shown that the expression is a multiple of 8. And so therefore it is true for n equals k plus 2. So we've done steps 1, 2 and 3, and we would now finish off with some conclusion that by the process of mathematical induction we have proven that this proposition is true for all natural numbers that are even. Alright, on to example 2. Show that 3 to the power of n plus 2 to the power of n is divisible by 5 for all n belonging to the set of natural numbers, this time where n is odd. So, step 1. Prove true for n equals 1. So we can start with 1 this time because 1 is our first natural number that is odd. So substituting in 1 for n, we have 3 to the power of 1 plus 2 to the power of 1. That's just 3 plus 2. 3 plus 2 is 5, and this is clearly divisible by 5. So therefore, the first statement is true. Alright, step 2. We need to assume true for n equals k. However, n equals k must be an odd number. So 3 to the power of k plus 2 to the power of k, we want this to be divisible by 5, so I'll express it as 5 times some other natural number p. And there is our step 2 done. Step 3. Prove true for n equals, once again, I want you to have a little think, what's it going to be? Do we go back to 1 because k plus 1 because we're dealing with odd numbers? No, if k is an odd number, which we've assumed back here in step 2, then the next odd number is going to be 2 further along from that. So once again, we want to prove true for n equals k plus 2. So what are we required to prove? 3 to the power of k plus 2 plus 2 to the power of k plus 2 must be divisible by 5. That is 5 times some value q, where q is a natural number. So we have seen previously how we can take 3 to the power of k plus 2 and 2 to the power of k plus 2. We can break these up. We looked at this method in the first video. So let's do that now. So we're undoing the index law for multiplication and addition. So we have 3 to the power of k multiplied by 3 squared, right? Combined, that gives us 3 to the power of k plus 2. And then likewise, we have 2 to the power of k times 2 squared. That gives us 2 to the power of k plus 2. Alright, well 3 squared is 9, so we have 9 lots of 3 to the k. And 2 squared is 4, so we have 4 lots of 2 to the k. However, remember we're trying to think how we can link this to step 2. And at the moment, there's a bit of an issue because in step 2 and step 3, we've got different bases. We've got a base of 3 and a base of 2. So what could we do there? Well, if we eliminate one of the bases through substitution, things might become a bit easier for us. Now, it's up to you, I suppose, to choose what you want to explore, but for now, we are going to make 3 to the power of k, rather, the subject, using step 2, and then we will eliminate 3 to the power of k. So, using step 2, 3 to the power of k is equal to 5p minus 2 to the power of k. So let's take that and substitute that in here for 3 to the power of k. So we'll substitute that in there. So we get 9 lots of 5p minus 2 to the power of k. And then we still have 4 lots of 2 to the power of k. And so while this is still a bit messy, at least now we only have one base, this base 2, that we're dealing with. Now remember, our aim is we just want to be able to drag a common factor of 5 out the front. So let's expand this and play around and see what happens. So we get 45 lots of p minus 9 lots of 2 to the power of k plus 4 lots of 2 to the power of k. And we can combine like terms here. If we have negative 9 plus 4, that gives us negative 5, and in this case, negative 5 lots of 2 to the k. Now, obviously 45 is a multiple of 5, so here we can drag 5 out the front. We're left with 9p minus 2 to the power of k. In other words, 5q. So we've done it. We've shown that this statement is a multiple of 5, and the little link at the end here is that q will be equal to 9 lots of p minus 2 to the k. Now, what if we went the other way? What if back here we actually made 2 to the power of k our subject? Like so. Well, if we did that, it would still work out nicely where we could drag out a 5. So in this case, it doesn't actually matter what method you choose. And if you'd like to have a go at that, I would encourage you to do so yourself. So back to the question itself, we would finish off with a little statement just saying that this is divisible by 5, or you could say that it's equal to the right hand side for what we were required to prove, and therefore it's true for n equals k plus 2. And once again, we'll finish off with an overall conclusion about the process of mathematical induction. So that's our 2 examples for this lesson. Good job. See you next time.